Hi, so in this video, we're going to continue taking our look at confidence intervals from a more classical approach in Chapter 7. And in particular, we'll be looking at section 7.4 in the book, which talks about confidence intervals for proportions and differences of proportions. So as the motivating example for the next several examples, we're going to take a look at a recent poll done by ABC News where, amongst other things, they asked people's opinions about how they felt about the coronavirus and how the U.S. response to that was going. And one of the questions they asked was, in the past week, have you worn a face mask or face covering when you've left your house? And so here you can see the breakdown by Democrats and Republicans. And so my favorite part, maybe I'm strange about all of these polls, is reading the fine print beneath it. So from this article that I've linked below, they have a little blurb on the bottom that talks about some of the methodology behind the survey. And in particular, they state that the margin of error of their survey was 5.3%, and their sample size was out of 512 adults. So here's the question that they asked. In the past week, have you worn a face mask or face covering when you've left home? And these are percentages of people, not total number of people, that responded yes, no, or did not leave home. And so they ignored the people that did not leave the home. And out of all the people that did leave home in the previous week, they then broke this down into, okay, out of the 512 people, 443 said they did leave the home. And out of these people that did leave the home, 55% said they did wear a face covering, 45% said they did not. So I want to focus on the data collected in this question over here. So we're going to ignore the people that said they did not leave the house at all. So our sample size here is 443, and the proportion out of that 443 that did wear a face covering was 55%. Okay, so this is going to be our motivating example, and we have discussed how we can create bootstrapping confidence intervals for proportion. And in today's slides, we're going to walk through how we can use more theoretical models to construct confidence intervals for proportions. So from the previous slide, we saw that we had a random sample that contained sample size N was 443 adults. And 55% of those adults responded that, in fact, they did wear a face covering in the past week. So if we wanted to use this data to come up for an estimate for the proportion of all adults in the US that wore a face mask in the past week when they left home, let's just kind of keep a couple of things in mind before we move on. And so the first question is saying, well, what's the correct notation for the proportion of all adults in the US that wore a face covering? So since this is referring to a population, we would want to use the parameter P to denote this. And the whole point here is we don't know what this value is. There's really no easy way that we could gather this information about all adults in the US. So instead, we picked the sample 55%. We picked the sample of 443 adults in the US, and we found 55% of them that did leave the house responded that they wore a face covering. So since this is referring to a sample, this is a statistic. And so to denote this, for example, we put hats over our values to denote an estimate. So this would be p hat, because this would not be the precise value for the population parameter, but kind of our first point estimate for that. And if another polling service goes out and conducts a similar survey, well, let's just kind of think about what changes in this scenario. So the value in part A, P, is going to be the same. So this is not random. This is a population parameter, not random, it's just unknown. Whereas the sample proportion is random, And so it's going to be different. But if we're picking our samples randomly, then there shouldn't be too much bias, and so it shouldn't be drastically different from the 55% that ABC News got. But there is going to be some variation from sampling to sampling. So the whole point is, when we give our estimate for the proportion of all adults in the US that wore a face covering, we wouldn't want to say it's 55%. We should say it's pretty close. We think it should be close to 55%. And the question is, how do we build in the error? How do we estimate how much variability we have due to the sampling process? And so to wrap up this introduction into this section, what we do know is that this sample proportion p hat, this 55%, is an unbiased estimate, point estimate for p. We've shown that already, that the expected value of p hat is p, so that's good. But of course, picking different samples, we're going to get different values for p hat. So what we'd like to know is, how can we get a sense of how far off our p hat is, our estimate is, from the actual value. And so one way that we've done this previously is to use bootstrapping. And we use the bootstrap distribution to estimate the sample distribution, and then we could estimate the standard error. Alternatively, as with means, we can use a theoretical model for the sampling distribution, namely the central limit theorem, to model what the sampling distribution should look like. So that's what I want to walk through in the next couple of examples.